All right, ladies and gentlemen, what to do now? So, good morning, you all at home. I hope you guys are nice and warm today. So, what I want to do here, remember this, we worked on finding the component of u along v, right? We did these, it's the shadow we talked about here. Find that shadow, and it's a scalar. And that's going to be an important detail, component of u onto v. So what I'm showing you guys here now, by the way, is kind of an application of that. So you have an application of determining the component of u along v, and I want you guys to know that you want to use this formula. That's the component of u along v, and that's a scalar value. You say a scalar value is a fancy way of just saying number. Okay, so it's a number, ladies and gentlemen. All right, scalar is a number. Now, you might say, how can we apply this idea of a scalar value, this number that we're looking for, the shadow or component of u along v? Here's an application, and I'm going to erase this because it's distracting me, but it's in your notes. And here we go, component of u along v. One of the reasons why we learn mathematics is so that we can work on the applications. Is that right? Do you guys know what I'm saying? Determine the component forces acting on a car with an incline. So we want to work on this application here, okay? And this is one of the reasons why we actually care about vectors, dot product, is to really work with the applications. And this is kind of what's going on. So I want you guys to understand something here, that cars have weight. And you might say they do. Yes, they do. And in this example, you have a what? The weight of a car. It's a 2,000-pound car. Here it is. Here's your car. And it's parked on a horizontal driveway. Now, that's an important idea. To say that the driveway is horizontal. Okay? So there's a horizontal line is what they mean. And that's a very important detail. Because when a car is on a horizontal driveway, all of that weight, and we represent this here, you see, this is like that point P in our applications. The weight of the car, due to gravity, is pulling down on the car. And that weight is represented by a vector, right? Because that has magnitude. And you go, what's the magnitude of that vector? There's your weight vector. Where the magnitude, there's a typo. Darn it. That should be 2,000. Okay. Ooh. 2,000. Note to self, fix those typos. So the magnitude of that weight vector is 2,000 pounds. Okay, you guys with me on that? So it's a vector that has magnitude and direction. Now you say, well, what in the world is this direction of this vector? Well, if I can do this here, draw a little, I don't know, ghost X and Y axis. Okay. The angle now, since we know the magnitude, is the standard angle. It's 270. So you say, okay, the magnitude of that wave vector is the magnitude is 2,000, the direction is 270. So we represent this as a vector, okay? Magnitude and direction. So if you guys recall, what have we been doing? We can describe this vector. I'll use W for weight. So if I put now the magnitude 2000 cosine 270 degrees I plus that 2000 sine 270 degrees J, this will give me the weight vector. And the weight vector will be, let's double check now, okay? We're going to use our calculator. Wake up, TI, wake up. And the TI is waking up. So you can say, okay, 2000 cosine 270 with 2000 sine what? 270. So this becomes 0I minus 2000J. And so the weight vector will be, okay, we can see this weight vector, negative 2000J. So what I did here is I summarized all of this information there to say to you guys that weight vector in blue now is minus 2000J. So if you were to graph this, the graph goes right here. There's that weight vector in blue, okay? You can see that there. And that's happening on a horizontal what? Ground. A car on horizontal ground. Okay, you guys with me on that? All right, there's the deal. There's the picture. Yeah, just kind of clean that up with the typos there on that, and I'll try to clean that up myself because those worksheets are online. And so, ladies and gentlemen, there you go. This is how we find the weight vector. We have the magnitude and we have the direction there. And there it is. We use this horizontal and vertical component form. 0. And, you know, we can label it there too. Okay, now you say, well, why do we have a picture here of an incline? And you go, well, cars don't always park on horizontal ground. Have you ever seen a car park on a hill? Yeah. So what happens if you take that same 2,000-pound car and now it's on an incline of 25 degrees. So you got this incline now, 25 degrees here. This 2,000-pound car, remember, is having all of its weight pointing down to the center of the earth. Is that true? So if you notice here in this picture, again, you have that weight vector going down to the center of the earth. And you go, okay, I see what's going on. Now, here's the thing though. if I start to now look at this a little differently, and I say to you, what if, and this is kind of, how to put this here. What if I look at this as maybe an x-axis here? Isn't my y-axis what? Perpendicular? Let me try to draw it. Okay. So here's my what? There's my point P. And I can now see this as like this x-axis and y-axis. And yes, it's tilted by what? 25 degrees. So you have this realistic picture that we're looking at now of a car on a hill. That's how they actually draw the incline and communicate that there's an incline. This line is called a horizontal. And there's a 25-degree angle there. Okay? So, what's going on with our vectors? So what I'm going to do here now is this. I'm going to get some pictures, like maybe, I'm going to draw like this picture for you guys. Isn't it true that that blue vector can be described as the sum of that orange vector with the green vector? Okay? Where my weight vector here in blue, this is that weight vector. And you go, oh, here's a weight vector. And the weight, again, it looks like we have that typo, is 2,000 pounds. So let's clear that up. So this is what they're kind of getting at. The question's going to be, what is the component form vector now? Oh, here we go. Let's look at my picture here. Okay? And so here's what we're going at. We can say, we can use some vector addition, this is what I'm saying, and some similar triangle information to determine component forces. What are the component forces for the 2,000-pound car with a 25-degree incline? So this is what I'm sharing with you guys. You got this picture here that there's these other force vectors acting on that, and it's just a vector sum. And so how you find that is to know, okay, let's draw that picture here, but I'm going to take this green vector and I'm going to move it up here. And I'm actually going to tilt it if I can. Let me see if I can redraw that. Let me undo that. And the green vector really looks like this. It's going along this axis here, okay? Because we can move our vectors freehand. And so isn't it true that the orange vector plus the green vector, isn't that the resultant vector W? And that's what I want you guys to see here, okay? That's the picture. You draw your x-axis and your y-axis. The W vector is still going down this way, okay? All right. And so that's what I'm saying here. This creates for us a triangle, though. And it creates this triangle, if I kind of draw it here. And that's the picture. And that's a right triangle. So the question becomes, what are the angles here in this right triangle. Now, this goes back to geometry, ladies and gentlemen. You go, what do you mean? The geometry course. In geometry, these triangles are similar. That 25-degree angle, ladies and gentlemen, will give you over here the same 25 degrees because of vertical angles. So we said, if you remember our discussion, those angles are vertical. And this triangle here now, if I change colors here, this is a right triangle. There's 90. That makes this angle have to be 65 degrees. Because of similar triangles. And if that's 65 degrees, if I draw another triangle, what color should we use? Maybe pink? This is 90 degrees. That will be 65 degrees as well. And by the way, this becomes 25 degrees in case you guys did not know here. And that's because you have these similar triangles here from geometry. So that 25 degrees makes this right triangle here, this angle 25 degrees. The complement is 65 degrees, and this is now all the information we need to project our vectors. Okay? And so we have in this picture U, vector U, and I believe that was horizontal, that was green, and orange, vector V. We're going to now project. And you might say, well, how do we project? We're going to find the component of W, that's the blue vector here, right? We're going to find the shadow. What's the component vector of W onto U? This shadow, that's going to be what we're looking for in green. So I think it's going to be better if I remove some of these things and say we're looking for the shadow here. And then we're going to look for the shadow over here. And that's all. So we want the component of W onto what? U. And that's now going to be, if I go back and I said, well, do we have to get everything in vector form to do that? And we can, although we can also use the what? The geometric definition of component form. Okay, the component of U onto V is the length of U cosine W. But if we're looking for the component form of W now onto, I guess it was U? It might have been U. We're going to do V shortly. Then we need the length of W. We have that. And the cosine of that angle between them. And we have that too. So in our notes, the reason you see in these notes for this example, 2,000 is because that's the length of what? W, the magnitude, and the angle between W and U here is 65 degrees. So it's important to find that angle. The angle between W and V is 25 degrees. So this portion is my component form 2,000 cosine 65, which will give you 845 pounds, approximated to the whole number, 845. Here's the thing. Over here, the component of what? W onto V is going to be what? 2,000 cosine of what? 25 pounds. $1,813. So, ladies and gentlemen, here you go. This is why you care about what? Finding the component form of these vectors here. So that's going to be the exercise here with these here. Okay? And so if you said, well, what about this other situation here? Right? What about these other two? How do we handle this? Now you have a 2,500 pound car on that 10-degree incline, right? How do you handle this 10-degree incline? It's going to be done the same way. So you have this vector W here. Okay, and you go, is that exactly the same picture? Well, sort of. 10 degrees. And if we create that X and Y axis, maybe, I don't know if we should use a highlighter, you're going to get this triangle again. And if we want to use our colors, I guess it was orange, right? Orange then. We got this orange portion here. Let me undo this. We're going to look for those component forms, those shadows. But you might say, well, what happens with this 10 degrees? Well, 10 degrees here, this angle right in here. The inclined angle of 10, because of all the similar triangles that I went through here earlier, is the same as this angle here, 10 degrees. And maybe we can't see it very clearly like that, but I'm going to do it this way. That's 10 degrees. But you might say, well, don't we need the angle over here? Like in this case, 65. Aren't they complementary angles? So if this is 10 degrees here, maybe I'll change my color. How about if I do it this way? No, we'll leave it that way. This will be the complement here. This will be 80 degrees. Because we're trying to find that complement angle to 10. It'll be 80. So that incline angle of 10 will go right there in the middle here. And that's what you need to find the component form now. So you can call this vector, let's be consistent. I think I called this vector in this other picture V, so it's U and V. U and V. So to get the orange shadow now, if we said, what's this shadow here? Well, that's called, we should say, the component of what? Of W onto V. Which would be the length of what? W. Cosine of that 10 degrees here. This is all that we need here. So this is the orange portion. Oh, I know about that. And so this would be 2,462. If we go to the whole number of pounds. So we're going to leave it that way. Component of W onto U is the length of W cosine 80 degrees. Now the length of W would be what? 2,500 cosine of 80. And we'll see what that gets us. £434. And that's the deal, ladies and gentlemen. So that 2,500 pound weight is really distributed with two real vectors. Okay, what do you guys think? I know you've seen a few examples on that. You got to see more. We're going to go through these examples, but these are applications of, it's really related to our dot product, and you'll see. Should we try one more? And you go, okay, what's the difference now? Now you have a what? A 3,250 pound car that's at a 15-degree incline. So again, you say, okay, here's that point. You got that 15-degree angle. When we draw that right triangle here, that 15 degrees goes where? Where does 15 degrees go? Right here. Is that right? And again, I'm going to just draw this line so I can put 15 degrees. What that means, though, is I'm going to have the component of W onto V. We're calling that V over here. There's a V vector. And the component of W, because this is W, onto what? This is my U vector. So to get the complement of 15, isn't that 75 degrees? Right? You say, what's the angle between W and U now? Right in here, that'll be 75 degrees. So in this example, 32,000 pound weight, that's the length of vector W, 3,250. And I think I'll just put the weight there, 3,250. You guys good with that? Using that definition of component. And there's my orange. And then in green, we'll put the green portion now. I'll say this will be 3,250 cosine of that 75-degree angle. And that's the component of W onto U. Okay. $3,250 cosine 75 and $3,250 cosine, I believe it's 15, right? Okay, so the first component is 841 pounds, right? And the second one's going to be what? 3,139 pounds. So, ladies and gentlemen, there is another example of finding the components of one vector onto the other, and that's an important detail. Easy peasy lemon squeezy. All right. Should I have you guys try the last one? I'm going to have you guys try the last one. Okay, so we'll go over it, but I want you guys to try that. And we'll see how this goes. Let's get out our clock, okay? All right, let's take a look. You guys ready for this? You guys ready? Okay, so create your what? Create your triangle. You guys okay with that? Then that's a right triangle. And hopefully the iPad will cooperate. All right, there it is. Your vector V, I believe we've been calling this vector V in orange, is down here. And then I'm going to put this vector here called U, which happens to be, by the way, the same vector here, just to kind of remind you guys, okay? Happens to be the same vector. We can move them freehand. And if we do that, we should probably make it the same exact length. $20 degrees. What's the complement of 20 degrees now? You guys remember? 70 degrees? Well, 90 minus 20 will be 70 complement. This is going to be the complement here, right? Because remember, this is also a right angle. So I got to try to write it so it's clear. What's that? Yeah. Yeah. So you're going to take the weight now again here, okay? $27.50, excuse me, cosine of 20 degrees. $27.50 cosine of 70 degrees. Okay, it's 2,584. $941. There you go, the component form. And this is why, ladies and gentlemen, again, that, you go through this component form. This is really the reason. And you do have something called, by the way, an application called work. And you go, what do you mean work? Yes, work, generally speaking, from first principles, is force times distance. So it's really force times the distance an object has moved will be your work. Okay, so it's a product. This is an application of science. Now, when you're having vectors, though, and you say, what about vectors? Well, you have a vector product called the dot product. So the amount of work, which is a scalar value now, this is a number now, because the dot product is a scalar. If you take that force vector and you multiply it by the distance an object has traveled, you get something called work. That's the value. And so you're going to use that very important fact. And so very often, you know, you might say, can you compute the work done on an object by the force F? Force is represented by a vector. And you just move the object from one point to what? Another point here. So they gave you a force vector here, okay? And now you might say, well, what's the distance vector, d? Well, the distance vector d, you moved an object from an initial point, okay, to a terminal point. So I'm going to find my scratch, and let's remember these points, 0, 0, 2, 6. So 0, 0, 2, 6, where's our vector scratch? That's not it. There you go, 0, 0, 2, 6. Go to 2, 6. 1, 2, 1, 2, 3, 4, 5, and 6. So we can get a d vector is what I'm saying. What's that vector d? Isn't it 2 minus 0 and then 6 minus 0? So that d vector is 2, 6. In ij form, it is 2I plus 6 what? J. Now, this is that d vector. And I guess, I don't remember what color I used, but okay. What was the force vector? Do you guys remember? Was it 3, negative 4? Or 4I minus 5j, and it was going to be green. So 4I minus 5j. 4I minus 5j. So that the work is force dotted with that distance. So you say 4I minus 5j. Let's get the dot product. So 4 times 2 plus negative 5 times 6. 8 plus negative 30 will be negative 22. So let's see, this is the d vector. Let's put this force vector in green, 4, negative 5. 1, let's see where this is at. It's a bit odd. Sorry, I think there's going to be, I have to change this on you guys. I apologize. I think there's a typo on this. This should be 4, 5. 4 positive 5. Okay, this would be a typo on you guys. Make that a plus. So that's 38 now. So 4, 5. Let me go back here. 4, 5. It has to make some sense. 1, 2, 3, 4, and then up 1, 2, 3, 4, 5. Okay. So it has to make this sense here. So you can have your object here, P. So that means now your work's going to be 38. Okay? Now you might say, if the force is in pounds and the distance is in feet, this is going to be 48. They call that foot-pounds. They just change the order in which they describe it, if I can. There you go, ladies and gentlemen. 38 foot-pounds. Easy peasy, lemon squeezy. It's a dot product, just so you guys know. So there's going to be, questions like that. You take the dot product. Let's look at the next one. Foot-pounds. Where are you? Could never find that. There we go. Okay. Let's try this one here. You got a force vector here. Just going to go back here if I can. Force vector. Now you're going to move the object from this initial point to a terminal point. And it seems to not really like to. Okay, so remember, negative 1, 1 to 201. Negative 1, 1 to 201, and I have to go to my scratch. Okay, so even if I bring in your picture for work here, okay, there's the initial point and then the terminal point, right? So this is going to be not to scale. Okay, so here's going to be where 201 would be. Anyway, let's find the vector. Let's find D. The distance traveled here will be 200 minus a negative 1, and then 1 minus 1. So the D vector will be 201 because that is plus, and then it'll be 0. So what I am saying here is that vector D is really right here. The point 201, comma 0. And that's what just happened. We found the vector D, the distance traveled here. Okay, now, do you guys remember what the force vector was? I guess I put it in green. What's the force vector? $200I50J. Okay, $200I50J. So let's find the work. So sometimes I can write it this way here, or sometimes I could write it this way. Then I'm going to do the 200I plus 50J dotted with 200I plus 0J, or just 200I. So this is going to be the dot product. Okay, let's get the work here. 200 times 201 plus 50 times 0. And so this is a lot of work. Pardon the pun. 200 times what? 201. That's going to be 40,200. And again, we're going to use foot-pounds here. Okay, so if that distance is in feet and the force is in pounds, you get, and that's not a vector, that's a scalar. Foot-pounds. So this is an application, ladies and gentlemen, of work. Did you guys see that in your study guide by any chance? Were there any work questions on your homework? I thought so. Yeah. Here's some more, but they're given to you in words. Some more given to you in words. Okay. Anyway. All right, ladies and gentlemen. Maybe we should do. What about this one? Number 21. The force is 4I minus 7J. It moves an object 4 feet along the x-axis. Okay, so 21. Moves an object what? 4 feet along the x-axis. So this is going to be, your starting point is 0, 0. This is the x-axis. This is 4. Now that endpoint is x is 4, y is 0. So the distance vector in this situation for number 21, that d vector, 4 minus 0, 0 minus 0, 4, 0. 4i. Force vector, 4i minus 7j. So what's the work going to be? It's the dot product, right? So you're going to take the force vector dotted with that distance vector. So it'll be 4 times 4 plus 0 times negative 7, which will be 16. Put it up here. Your work is 16, and again, we'll do foot-pounds. There it is. Okay, you guys okay with number 21? See how it moves that object? You get the distance factor. What do you guys notice about 22? 22 is done the same way. Is that right? So in 22, the force vector is 2i plus 8j. Your distance vector will be 11 minus 2i plus 13 minus 5j, right? You're getting the ij form. And I'm going to get rid of all the work in 21. It's in your notes. It's in the video. Okay, so let's see what that d vector is. Nine I plus, what's 13 minus 5? Isn't that 8? 8j. So your work is force dotted with the distance vector. Okay, so you're going to take the components. 2 times 9 plus 8 times 8. That will give you your work. 18 plus 64. What's your work going to be? 74 plus 8 is 82. We'll stick with the foot-pound unit. And this is question number what? 22. Okay, you guys okay with that one? So let me see your book here. Assignment, homework 5. So I'm going to get rid of this here. And then what days are final? Do you guys remember? Tuesday. What month are we in? We are in December. Thank you. December 12th at 7 a.m., huh? All right. And what's today? Anybody know what today is? December 7th. Anyway, you got some homework on vectors. I don't know. I thought I seen really weird. Got to double check. Let's check the textbook. I think here, homework 5 will say 39-2.